Hi, everyone. My name is Elizabeth Kreitz. I'm a postdoc in the Information Security Group at University College London. I recently graduated with my PhD in math from Brown, and I actually did part of my bachelor's in math at McGill. So I was really looking forward to meeting everyone in Montreal, but I'm glad that at least we can connect online for now. So today I'm going to be talking about work on reputable list curation from decentralized voting. This is joint work with Mary Maller, Sarah Meiklejohn, and Rebecca Mercer. So does anyone recognize this photo? Maybe not, but it was actually the #1 restaurant in London in 2017 as ranked by TripAdvisor. If you find that hard to believe, that's because it was a hoax. The person behind the hoax, Uba Butler, created The Shed at Dulwich and wrote a bunch of fake reviews for it on TripAdvisor. He had been writing fake reviews on TripAdvisor for restaurant owners who paid him $13 per review to write positive reviews of restaurants that he'd never even been to. So he wondered, in the current climate of misinformation, is it possible to fake a restaurant? After The Shed reached #1, he did actually open for one night and served customers frozen dinners. After he revealed the hoax, there was a media storm, and he was asked to do interviews all over the world. He actually ended up sending lookalikes in his place. So The Shed calls into question the trust that we place in certain authorities to convey accurate information. And the goal of this work is to show how we might curate a reputable list in a decentralized environment. Now, decentralization lowers trust in authorities, but having no trusted authorities at all is problematic. So if we're trying to create a list of good restaurants, of course, we want the reviews to be written by people who actually have been to the restaurants, but relying on the wisdom of the crowd is risky as it can be gamed. This was the case with The Shed. The rise of misinformation online could be attributed to a lack of authoritative sources of information or a disagreement about who those sources should be. So we can have a set of curators who are semi-authoritative for a particular list. One example of a decentralized list curation in practice is the New York Times News Provenance Project, which aims to identify real images online. So as a photo circulates around the web, it's often stripped of its context, and this opens the door for all kinds of misrepresentations. The question is, how can we curate a reputable list in this context? So we begin with a set of curators, such as the New York Times, The Guardian, and The Washington Post, who apply to become a curator of a specific media repository. Now suppose that a photographer applies to have a photo included in this repository, but that Le Monde thinks there are inaccuracies with the photo and challenges its inclusion. At this point, we can create a poll and the news organizations can vote. At the end of the poll, the photo is included in the repository if, say, the majority of the news organizations vote for its inclusion. So this is a photo on a social media feed claiming to show the devastation after a tropical storm in Florida. However, the photo was actually taken in Missouri over a year ago. This shows how curation by news organizations might provide verifiable and user-friendly signals about the authenticity of photos. A prototype of this kind of curation was built by the News Provenance Project on top of IBM's Hyperledger fabric. When curating a list, it's important to think about the privacy implications. The business interests, social relationships, and potential conflicts of the participants can skew the voting. For example, if we're curating a list of the best new chefs in the city, a chef might expect their friends in the restaurant industry, who are curators, to vote for them. There can also be outright retaliation or bribery. It's essential that the curation decisions are kept secret so that the parties can vote honestly. So one way to curate a reputable list is using a token curated registry, or TCR. And this is what we focus on in this work. A TCR has two main types of participants. It has services, who apply to have entries added to the registry, and curators who decide on what content can be added. A user becomes a curator by depositing tokens into a smart contract. When a service applies to have an entry added to the registry, it also places a deposit and starts a timer indicating how long the curators have to challenge its inclusion. If enough time elapses and no curator challenges the inclusion, then the entry is included in the registry. However, if even one curator challenges its inclusion, then they also place a deposit and open a poll to allow the other curators to vote. Again, this comes with a timer indicating how long they have to do so. Once the poll is closed, the contract can tally the results and reward the curators who voted with the majority decision, or whatever rule is specified in the contract. If the vote is on the side of the service gets back their deposit and some portion of the challenger's deposit. The remainder of the challenger's deposit is split between the curators who voted in favor of the service. If instead the vote is against the service, then the situation is reversed. So the challenger gets some portion of the service's deposit, and the rest of the service's deposit is split between the curators who voted on the side of the challenger. Now, it's important to remember that tokens don't necessarily equal money, so they could actually represent something like reputation. For example, a Michelin star inspector might have more tokens than a local restaurant reviewer. So there are some partial solutions for how to construct a TCR. For example, Consensus uses a two-round commit and reveal approach called partial lock commit reveal. In this case, the voting proceeds in two rounds. In the first round, the vote is sent as the hash of the vote plus a random nonce R, and in the second round, the vote and the nonce R are revealed. Once the poll closes, the votes are tallied, and if a curator's vote matches the outcome, it's rewarded. The civil project, which recently merged with Consensus, was backed by a TCR and used the partial lock commit reveal approach. The trouble with this approach is that it reveals the votes in the clear, so it offers absolutely no secrecy. Alternatively, the secret voting protocol due to Enigma focuses on secrecy, but unfortunately it relies on trusted hardware to securely tally the votes, rather than allowing this to be done in the clear. So let's take a closer look at what properties might be desirable for the voting protocol, which is the core of the TCR. While it might be tempting to pick a voting protocol from the literature, we require specific properties for our TCR. The first property is vote secrecy, and this says that you cannot learn how a user voted beyond what you can infer from the tally. So, for example, if the tally were 0, you could learn that everybody voted 0. In our example of curating a list of the best new chefs in the city, chefs would be very upset to learn that their friends in the restaurant industry may not have voted for them, so it's absolutely critical that the votes are kept private. Another property is dispute freeness, and this says that it is publicly verifiable whether or not everyone has followed the protocol. Unlike in a traditional voting scenario, it's already publicly verifiable whether or not the contract follows the protocol, since its code is visible. So we only need to consider whether or not the curators are behaving and punish bad behavior appropriately. The final property we need is self-tallying. There's no natural trusted party to compute the tally. And specifically, in order to deploy a TCR as a smart contract, the contract must function as an untrusted authority and must operate deterministically. For voting, this means we require a protocol that allows anyone to compute the tally once everyone has voted. Prior to this work, it was not known which security properties are important for TCRs, and existing constructions do not achieve strong or provable notions of security or privacy. In this work, we provide a formal cryptographic model for TCRs in terms of the two security properties that they require. vote secrecy, and dispute freeness. Our definitions include a formal game-based treatment of the interactions with smart contracts and of the voting mechanism. We also provide the first TCR construction that is provably secure. In particular, the security and privacy of our TCR can be proved under the decisional Diffie-Hellman assumption in the random oracle model, and we can run it using a transparent setup. We also provide an implementation, which shows that our construction is practical enough to be deployed on a constrained, decentralized platform like Ethereum. So let's now talk about our construction of a TCR. I'd like to focus on the more cryptographically interesting aspects, which are the deposit, voting, and payout mechanisms. A user becomes a curator by depositing some number of tokens, and this creates a commitment to their balance. As curators earn tokens, they can update the balance in this commitment. We'll see shortly how they can do this in a privacy-preserving way. But for now, let's take a closer look at the voting mechanism. As a starting point, we consider a voting protocol by Howe, Ryan, and Zielinski, which satisfies some of the properties we require. The voting protocol proceeds in 2 rounds. The first round acts as a registration phase. Each user samples a random value x and then forms a registration key, which is g, some generator, to the power x. They then give a zero-knowledge proof of x to show that C0 was formed correctly. The second round is the voting phase. At this point, the set of registered voters is fixed, and we need a fixed set of voters in order to achieve the self-tallying property, which says that the tally can be computed by anyone, and in our case, the contract. So since all the registration keys are fixed in the second round, each user can form a value y, which is a product of the registration keys of all other users. They use this to form their vote. So their vote has the form g to the vote, y to the x. They give a zero-knowledge proof that the vote is a Boolean value. We can consider more general votes, but for simplicity, we'll assume that votes are Boolean. Y has this particular structure because it enables self-tallying, which we'll see in the next slide. This voting protocol was implemented on Ethereum by McCory, Shahadashti, and Howe. Let's show that the Howe protocol satisfies self-tallying. So consider a set of 3 voters. In the first round, each voter has formed their registration key. These are the C0 values. In the second round, they form their Y values, which are products of the registration keys of the other users. So for example, if we were to compute Y1, it's a product of voter 2's registration key and voter 3's registration key. Notice that these values are minus in the exponent. For voter 2, it's a product of x1 and minus x3. And for y3, positive x1 and positive x2. In order for voters to form their votes, they actually need to form y to the x. So let's take a look at those values. There's an important thing to notice for each of these values, and that is the cancellation of the exponents. So we see for y1, we have a minus x1 and a minus x2, and then for y2, we have positive x1, x2. This is how we can compute the tally. So we form a product of the votes, g to the vote, y to the x, for all 3 voters. And because of this cancellation property, the product of y to the x is actually 1. And that means what we're left with is g to the sum of the votes. So we can find the tally by brute force. And this is because the number of voters is limited. This fits the need of a token-curated registry, in which the set of possible voters is limited to users who, number 1, possess a specific token, and number 2 have chosen to use that token to act as a curator. To make this more efficient, the tally can be computed offline by one of the curators, for example, and then it can be verified that it's correct. Unfortunately, the How-It-All protocol doesn't achieve the properties we require. For one, the protocol lacks a formal proof of security. It seems very hard or impossible to prove vote secrecy. There is also no model of dispute freeness. However, the protocol does satisfy self-tallying. Our TCR construction is as follows. Let's start with the voting protocol. Our voting protocol again consists of 2 rounds. In the first round, users form their registration keys, but they also register their vote intention, which is a commitment to their vote. They then give a zero-knowledge proof that their registration key was formed correctly. In the second round, once the set of registered voters is fixed, voters can vote a second time. The tally can then be computed using the votes cast in the second round, the C2 values, as before, but the votes cast in the first round can be used to pay voters on the winning side. In the second round, a user must also give a zero-knowledge proof that the same value X is used as randomness in the first and second rounds, that the commitments C1 and C2 to the votes in both rounds contain the same vote, and also that this vote is 0 or 1. If the proof is invalid or a voter doesn't send a second round vote, the contract keeps the deposit as a form of punishment since it cannot complete the vote. You may be wondering how it's possible to pay each participant in a privacy-preserving way. After a poll, the contract can easily send the service and challenger deposits to the right places because these are public. So the question is how to pay voters who are on the winning side without knowing how they voted. Well, we have a trick for how to do that. Recall that initially a voter makes a deposit. This is a commitment to some amount of tokens. For the payout, we'll use the commitment to the vote formed in the first round. Let's say the goal is to pay 1 token if a user's vote equals the outcome, and 0 tokens otherwise. Since votes and outcomes are 0 or 1, we can consider the Boolean expression B1 equals B2, which can be represented numerically as follows. Since the outcome is known, we can form a commitment to this expression and combine it homomorphically using C1, and then fold the result into C. This has the effect of adding 1 to the balance in C if the expression evaluates to 1, meaning the vote equals the outcome, and 0 otherwise. The user can update their commitment with the appropriate balance and randomness R plus or minus X. While this would work with either C1 or C2, it is important to use C1 for payout because the base Y has a discrete logarithm that is unknown to the curator. So if we use C2, they would no longer be able to update the commitment. We're able to show in this work that under the decisional Diffie-Hellman assumption, our construction satisfies vote secrecy and dispute freeness. While dispute freeness was relatively easy to show, proving vote secrecy was quite challenging. Finally, I'd like to talk about the implementation of our TCR on Ethereum. We implemented deposit, updating the balance and the 2 vote phases on the curator side, and each of the corresponding verification functions on the smart contract side. We used 256-bit primes and the BN256G1 curve. This table shows the average runtime in microseconds, averaged over 300 runs, and the gas costs associated with each stage. At the time we wrote this paper, the conversion rate was $223 per Ether. It's currently about $245. Future work. It would be nice to incorporate some different proof techniques to make our TCR more efficient. And an important line of work we considered while writing this paper was how to prove concurrency not in the UC model. So concurrency allows multiple sessions of the TCR to be run at the same time while preserving security. Our vote secrecy proof limited us to a single session. However, in a follow-up work, we were able to devise a new construction of a TCR that achieves concurrent security. And that concludes my talk. I hope I've encouraged some of you to work on TCRs. And if you have any questions, feel free to send me an email. Thanks so much.